Well, this is the continuation of error back propagation training algorithm. We have seen if the activation function is 1 by 1 plus exponential of minus lambda net, delta OK will be equal to dk minus OK into 1 minus OK. If the activation function chosen is bipolar continuous activation function, that is 2 by 1 plus exponential of minus lambda net or minus net minus 1. Here lambda is chosen as 1. Lambda is the steepness factor. Okay, f of net equal to 2 by 1 plus exponential of minus net minus 1. Okay, so first order derivative of this one is f dashed of net, which is equal to 2 exponential of minus net by 1 plus exponential of minus net whole square. And further simplification, see here how I have simplified this. 2 exponential of minus net by 1 plus exponential of minus net whole square can be written as so half into 1 minus exponential of minus net by 1 plus exponential of minus net whole square. So when I square it and perform the take the LCM and perform the simplification, it comes as 2 into exponential of minus net by 1 plus exponential of minus net whole square. But what is this 1 minus exponential of minus net by 1 plus exponential of minus net? This is nothing but half into, this is 1 minus O. So this is O. So how is it O? So see this 2 by 1 plus exponential of minus net minus 1, take LCM, 2 minus of or 2 minus 1 minus exponential of minus net by 1 plus exponential of minus net. That becomes 1 minus exponential of minus net by 1 plus exponential of minus net. So that is nothing but O, which is nothing but f of net. Okay, right? So this is nothing, this entire thing is nothing but O. So that is half into 1 minus O square. Okay, so see here 2 into exponential of minus net by 1 plus exponential of minus net whole square is nothing but, so this is nothing but f dashed of net is nothing but half into 1 minus O square. So what is your, as seen in the earlier slide, what is delta OK? Delta OK is dk minus OK into f of net. So you have f dashed of net. If you have chosen a unipolar activation function, your f dashed of net is OK into 1 minus OK. If you have chosen a bipolar activation function, it is half into 1 minus O square. So now see here, so delta OK, since we have chosen a bipolar activation function, in this case delta OK is equal to half into dk minus OK into 1 minus OK square. So see that half into 1 minus O square is f dashed of net multiplied by dk minus OK. So delta OK equal to this one. The error signal term of the hidden layer, what we are seeing, we have seen the delta OK, that is the error signal of the output layer. What is the error signal of the hidden layer? I don't know the desired output here. What I need to do, I need to use whatever the error signal I get here, learning signal or the error signal I get here, in updating the interconnection weights W. So delta Yj is half into 1 minus Yj square, same, half into 1 minus Yj. Why you have considered Yj? Yj is the output. Okay, f dashed of net is half into 1 minus O square, is it not? Half into 1 minus Yj square, half into 1 minus Yj square. You don't find this term dk minus OK, so you will have sigma k equal to 1 to k delta OK. So this is considered, this is propagated backwards. Okay, delta OK into Wkj. Right, so delta OK we have found, delta Yj we have found. Step number 5 is output layer weights are adjusted. How do you adjust the weights here? Output layer weights are W. How do I update these weights? New weights are nothing but the old weights plus the change in weight, delta W. Okay, so that is nothing but Wkj new is equal to Wkj old plus the change in weight, delta W. What is delta W? Delta W, you know that it is the product of the learning rate, the learning signal and the input. Okay, so W corresponds to the interconnection weights between the hidden layer and the output layer. Okay, right? So what is the input corresponding to this? Y. Okay, so product of the learning rate, the learning signal delta, okay, multiplied by the inputs. What are the inputs? Y. Okay, so see here, updated weights, W new weights, Wkj is equal to old weight Wkj plus product of the learning rate, the learning signal, and Yj. Yj is the input. Now what are the hidden layer weights? Hidden layer weights are also to be adjusted. Here hidden layer weights are nothing but V. Okay, so Vji new equal to Vji old plus once again product of the learning constant delta Yj and Zi. Zi is the input to the hidden layer, is it not? So step number 6 is over. Once I continue till step number 6, check whether P is less than P or not. That is, you need to check whether the training pairs are still available or not. If the training pairs are completed, then go to step number 2. Okay, if the training pairs are completed, go to step number 8. If the training pairs are not completed, go to step number 2. Once again, do all these calculations. Okay, so once all the training pairs have been submitted or have been applied, okay, go to step number 8, which is the completion of the training cycle. Now we need to check for the error. The obtained error is compared with the maximum error which we have initialized here. See here. Eta greater than 0, Emax is chosen. Okay, clear? So maximum error is Emax, the obtained error is E. Okay, as we have done it here. So that is compared with E is compared with E maximum. If E is less than E maximum, that is the obtained error is less than the maximum value which is defined by you, then you can terminate the training and output the weights W, V as well as Q and E. Suppose if the obtained error is greater than maximum value, what we need to do? Training is not yet completed. So what we have to do? Then we need to go to step number 2. Once again, follow all the procedure. So this is how the training of the neural network takes place. Okay. So there is a flow chart related to this. You can see here. This is the flow chart. So what is step number 1? Try to recollect what is step number 1. Step number 1 is you have initialized the weights W and V. Okay, so step number 2 is you have to start training. Step number 2 is start training. Submit pattern Z, compute the outputs Y and O. You know how to find out the outputs. Output of the hidden layer Y, output of the output layer O. You have computed in step number 2. This is very easy to understand. The flow chart itself is so easy to understand. So first step is initializing the weights W, V and the maximum error and all those things. Okay, and the learning constant should be chosen greater than 0. Usually learning constant is in between 0 to 1. Okay, and step number 2 is calculating the output of the hidden layer Y and the output of the output layer O. Step number 3 is you have to compute the error, cycle error. Okay, new error is E plus half into D minus O whole square. Okay, and next step is you have to calculate the error signals, that is delta OK and delta Yj. Delta OK is half into dk minus OK into 1 minus OK square, and delta Yj is half into 1 minus Yj square into sigma delta OK delta OK into W. Okay, right? And Step number 5 is adjust the weights of the output layer. First of all, adjust the weights of the output layer. That is, updated weight W is equal to, or the new weight W equal to old weight plus the change in weight delta W, which is nothing but product of eta, delta and y. Okay. Now adjust the weights of the hidden layer. V equal to V plus eta delta y j into z. Okay. If more number of patterns are available, if it is yes, go to step number 2, perform all these things to complete a cycle of training. Okay. So new training starts here. Suppose if there are no new patterns, then check for the error. If error is less than E maximum, and you can stop training. If the error is greater than E maximum, you have to initialize once, you have to once again reset error is equal to 0 and go back to step number 2 and follow all this procedure. Okay. So students, this is error backpropagation training algorithm, okay, which is, you know, a very popular algorithm to train multi-layer neural networks. Thank you.